Good day to all of you. I'm very lucky to present to you my presentation that was made on 26th May 2022 at Prague at the IABSC International Symposium yesterday evening. Today it is 27th May and I'm dedicating that presentation made yesterday at Prague to our Honorable Minister Nitin Gadkari ji on his birthday. Thank you, sir, for your encouragement and being our mentor.
Good afternoon to you all. I'm Sachidananda Joshi, and my topic for the day is enhancement of Indian bridge management system using analytics within BIM data model. Bridges connect two communities. They connect residential and industrial areas. They enhance the landscape of the city. BMS the world over was initiated due to the collapse of Silver Bridge in USA. IBMS, also Indian Bridge Management System, or in short IBMS, owes its initial conceptualization to also the tragic loss of 26 young kids. Conceptualization started in 2003 post Damanganga Bridge collapse, in which these 26 school children died. It was a tragic incident. We started the conceptualization and we conceptualized IBMS as a linear path protocol. All basic data were collected under inventory. The inspection resulted in detailed observation. Testing on the bridge helped us to define the remedial measure and the required budget. All other modules and analytics analysis was dependent on the database structure that was basically two-dimensional. Preliminary assessment resulted in assignment of ratings for structural, functional, and socio-economic parameters. Ratings were assigned based on visual observations only. The rating system that we adopted was from 0 to 9. 0 indicated critical state and 9 indicated excellent state. These were used in progressive decision making process. Because they were used in progressive decision making process, consistency and correctness during assignment was critical. What were the shortcomings that we identified during implementation? We realized that within the IBMS linear protocol, there was no review and validation protocol. IBMS was dependent on symptoms for decision making. Within IBMS, it was possible to jump to the next module. This resulted in missing important information, and the emerging technologies rendered our protocol redundant. What emerged out of the upgrade was called as a unified bridge management system like UBMS. One must realize that bridges, like all structure, deteriorate with time. Our system needs to mature with ongoing research and focus on the final aim to prevent such loss of people that occurs due to collapse. UBMS is an intermediate step in this ongoing research. So what is UBMS? In inspection process, the inspector is at close quarter with various components, making it possible to correlate various symptoms and create his prognosis about the possible cause of distress. This is something similar to when you go to a doctor, the family doctor makes his prognosis and then sends you one step forward. EN 1504 published in Europe defined three processes of distress. These three processes were physical processes, chemical processes, and mechanical processes. Further, in our handbook for implementing IBMS/UBMS, we defined 11 causes as sub-processes or class causes within the physical, chemical, and mechanical processes. Based on the prognosis of deterioration, the inspector assigns rating from 0 to 9 for various sub-processes in which results in a matrix called the cause matrix. Once the preliminary and secondary causes are defined, we need to determine the deterioration process. For correct estimation of deterioration process, multiple observations are essentially compared to define the probability of a particular type of deterioration process occurring over a period of time. This leads to estimation of balance service life of the bridge, which can be made for various factors affecting the bridge structure. Evaluation of balance service life estimates the risk involved. Structural behavior is based on location of the loading and the reaction of this loading to various other factors, with the discontinuity in the section subjected to loading. Location of such discontinuity also affects the response of the section. One has to realize that the behavior of the structure is dependent on the geometry and various other conditions, including the geometrical location of the discontinuity. Location of the damage being critical to structural evaluation and determination of deterioration process. Modes of failure are also location dependent. It could also affect the load capacity evaluation of the member along the length of the element. None of the existing bridge management system, including BMS, is able to provide accurate digitized data relating to the location of the damage or distress. They have sufficient data regarding the cause of the distress and other related factors to enable deterioration modeling to be done. But the critical aspect of the location or of the damage or distress is a gray area. Research is ongoing. It is impossible to correlate exact location of previous distress symptoms over present symptom location because the data is based on database. This hampers the correct evaluation of deterioration model. This results in the engineer's inability to correctly evaluate the reduction in load capacity, and these shortcomings of bridge management are being sought to overcome using various presently available technologies and ongoing research. So, what are the new technologies that have emerged? Advent of unmanned aerial vehicles or UAV changes the way inspection can be done. We can use drones to capture still photographs or videos of bridge component and are useful in indicating the location and extent of distress. We can prepare 3D model based on such videographs and photographs, and these models are termed as bridge information model. Comparison of year-on-year photographs and video can indicate the progression of distress. Such data could provide important time series data for training artificial intelligence and machine learning that can be used for the evaluation of a realistic deterioration model. Spatial data, when connected with GIS, can be a valuable data for the bridge structure for determining the distress and the progression of distress over the years. How can we correlate this? Photogrammetry is the next tool for 3D modeling. Photogrammetry can make 2D or 3D models and take measurement using photographs and video files. This technology, in conjunction with the drone captured data, helps in the creation of geospatial 3D geometrical model. We All these models are purely geometrical model. We can integrate this with the bridge management system. So this brings us to an important question: why is bridge information model required, and is it the final destination, or is it sufficient? UBMS system is a cost-based management bridge management system, and it relies on symptoms resulting from 11 deterioration processes. BRIM or BRIM or Bridge Information Model relies on design data to establish the response. This response can precisely establish the deterioration progression. But one factor has to be remembered: design data is only available for very few bridges, and this design data can provide reliable information only for a selected cause system. Design data can rarely provide accurate prediction relating to the chemical processes. When we analyzed our data for over 35,000 bridges, chemical processes were identified as the main reason for deterioration in over 60% of the bridge showing distress in India. Within UBMS, the digitized data collected for distress location is purely descriptive. We would still need to be able to correlate this data with the image library. No design details are available, and that is a major hurdle in India. In the absence of this, the model that we prepare can only be a geometrical model and cannot be a performance model or a digital model. With the challenges enumerated above, our concept proposes partial integration of UBMS with bridge information model. The scheme proposed is to adopt principles used in the development of BRIM and evolve functionalities within UBMS to make it more workable. So, what is partial integration and how is it achieved? First, we come to the first point is creation of bridge information model. Data is available in UBMS relating to the number of spans and the geometry within these spans. Based on the data relating to the configuration of the element, we can create a schematic 3D model of the bridge. This is a geometrical model and it is not a digital twin. Various photographs of the bridge are then attached to the bridge information model. For elements which show distress, continuous photos or overlap are used to create 3D model which is only for that distress element. This 3D model is created based on drone captured videos or photographs. This model created is for one distress element with detailed of location of distress in the element. Since it relates to the location of distress in the element, we have termed it as LODE 3D model. Creation of such LODE 3D model using real-time photograph ensured that correct and precise location of the distress is captured. These models are small in size and for individual members. These models can be stored with the element number being used as a file name followed by the year of inspection. 3D model for various distress elements are stored in UBMS database as per the year of inspection. Two important usages emerge from this creation of bridge information model. Firstly, the overall distress progression for the whole structure can be evaluated. Based on the model, the successive inspection, a time series progression of distress for that element can be generated. Second important use of load model is in evaluation of quantities for various items of repair interventions. Load model is used for further analysis of distress in the bridge and the impact of such distress for the performance of the bridge. This evaluation is critical for decision making. Capacity evaluation essential can also be integrated once we have the design data. This is unavailable in an Indian scenario. The proposed protocol for evaluation has essentially three steps. First step is to determine the element which show worst or severe distress. The second step is to install structural health monitoring and monitor such identified critical element for 72 hours under normal live load. The third step is evaluation of deterioration process to identify the cause of deterioration based on collected information. Most of the processes of deterioration can be very well initiated, and progression path can be easily captured. The analytics provide additional data related to the distress and over time to enable authentication. Based on the result of the first cycle, the periodicity of all further monitoring can be done. Coming to the final conclusion, the concept involves creation of bridge information model. To this bridge information model, we attach location of distress in element model or load model. Study of load provides us with detail of critical damage elements. All such critical elements show distress symptoms. Showing distress symptoms are structurally health monitored for 72 hours. The evaluation of deterioration and its progression being realistic will yield sufficient data. Future scope involves use of artificial intelligence and machine learning. Research is an ongoing process leading to maturity of the established system, resulting in reliable and increased efficiency of the system. Result can be delayed, but accuracy can be achieved. Thank you for having a patient hearing. Thank you.